Welcome back, Chemistry Theory. This is EQ2.5, the last section of the EQ2 unit, Precipitation of Ions. So here we'll look at whether a precipitate will form when solutions are mixed by comparing something called the Q and the KSP values. So last time we looked at solubility, molar solubility, when there's a common ion acting. The last kind of scenario we look at with solubility equilibrium is this, and looking at whether something dissolves or not. So equilibrium can be achieved starting with the substances on either side of a chemical equation. For example, the equilibrium that exists between barium sulfate and the barium and sulfate ions. So in this equilibrium, so barium sulfate solid placed in water and dissolving. So that's the equilibrium equation. So it could be started with ions in solution going and forming a solid on the bottom, or a solid being introduced to the liquid and dissolving into barium and sulfates. So it can be either achieved by starting with barium sulfate or by starting with barium and sulfate. If we mix, let's say, barium chloride with sodium sulfate, we see something here. In the barium chloride, we have barium. In the sodium sulfate, we have sulfate. So barium and sulfate can come together and possibly form a solution on the bottom, or a precipitate, a solid on the bottom, I mean. So we have to see whatever we have in our solution, it'll be a certain value which we'll call Q, and we compare that to the solubility product. So the solubility product is a number that represents how much is capable of being dissolved. So if I have more than that maximum amount, then I'll have a solid on the bottom, incapable of dissolving. So over here, we'll put a big star over here. So if Q is equal to the KSP, it's saturated. That's a perfect amount for this scenario. My barium multiplied by my sulfate equals a certain number. If that value is achieved in a solution, then it's a saturated solution. But if I have more than is capable of being dissolved, I'll have a precipitation being formed. So solid forms out of solution. And it does that until Q and KSP equal the same thing. And if I have less than kind of that maximum amount, that number that represents the maximum I'm capable of dissolving, then that means I can increase the amount of barium and sulfate I have until they're equal. So that's what this scenario deals with. And we'll look at one example here, and then on the assignment I think there's about 4 examples, but the process is very similar. So we'll look at this example. Does a precipitate form when I have 0.1 liter decimal 008 molar lead nitrate added to 0.4 liters of sodium sulfate? And then here I'm going to give you a hint with all these types of questions. Sodium nitrate is soluble, but lead sulfate is not very soluble. So most of it exists as a solid in equilibrium with the solution. It has a KSP of that. So if I'm talking about lead sulfate not being very soluble, I have to figure out how much lead and how much sulfate is going to be in my solution so that I can see, does my value, is it equal to the KSP, greater than or less than? And again, if that Q is bigger than the KSP, that means I have more ions that are capable of making a saturated solution, so the extra solid will remain on the bottom. Right, so in this scenario I have lead nitrate, PbNO3, aqueous, and I'm combining that with sodium sulfate. Okay. Now, of course, it's lead 2 nitrate, so lead 2 sulfate, sodium ions, nitrate ions. So those are all from your pink periodic table. So if I look at here, lead and sulfate can come together and make a, let's see, +2, -2, so it says PbSO4. That's the solid that is going to form in the bottom of the beaker if I have enough ions. Then, of course, the leftovers, sodium and nitrate. +1, -1. and that's just aqueous. Okay, 2 nitrates, 2 sodiums. There we go, and I think it's all balanced. So what I have to do is I have to figure out how many moles of this I have and how many moles of this I have. Then I'm going to figure out how many moles of individual lead ions and sulfate ions, and then I'll be able to figure out the rest of the question. So I have to kind of break this into 2 parts. Look at this. Look at lead nitrate. What I want to do, I'm going to use the old equation that we used previously. Molar concentration is the equal number of moles of solute per volume of solution. And I'm given the molar concentration, 8.0 times 10 to the minus 3. And it's 0.1 liters. So I can solve for N, multiply each side by 0.1. And of course what that gives me is 8.0, one more decimal place moved, moles of lead nitrate. Okay, I'm going to do the same thing with sodium sulfate. So C equals N over V. The concentration of sodium sulfate is 5 times 10 to the minus 3. My volume is 0.4 liters. You have to have that in liters. Multiply each side by 0.4. And N works out to be 2.0 times 10 to the minus 3 moles of sodium sulfate. Okay? So that's fine. I know how many moles of compounds I have, but of course what I need to find is the ions that make up the not very soluble substance. So I need to figure out how many lead ions there are and how many sulfates. So it involves looking at how lead nitrate breaks down in a solution. So lead nitrate, of course, if it's a solid, it breaks down into lead 2+ ions and NO3 ions. So of course lead is 2+, nitrates -1, but of course you need 2 nitrates for every 1 lead. And of course how this works, if I have 8 times 10 to the minus 4 moles of lead nitrate, for every 1 mole I get 1 mole of lead, 2 moles of nitrate. So if I have 8 times 10 to the minus 4, I have 8 times 10 to the minus 4, and doubled 16 times 10 to the minus 4. I'll leave it as improper scientific notation so you can see that this number is doubled this. And of course, this is the one I'm looking for. I want to see how many moles of lead do I have in this solution. And doing the same thing here with sodium sulfate. Sodium sulfate in solution breaks down into sodiums and sulfate. Okay, and I need 2 of them here. For every 2, because this is +1, this is -2, so I need 2 sodiums. And according to this, I have 2 times 10 to the minus 3 moles of sodium sulfate. And if I look at the ratio here, 1, 2, 1. Therefore, 2, 4, 2 times 10 to the minus 3 moles. And of course, I am looking for sulfate. So I have the number of moles of each of those amounts. Okay? And so you can imagine this as I have lead nitrate and I have sodium sulfate, and I'm going to pour them together. And of course what happens is that the lead and the sulfate can come together and make a precipitate. So in order to figure out the KSP, of course what I have here is I need to figure out, well, what is the solution? What is the molar concentration of each of these? So one other piece I need to do is figure out the total volume of solution I'm going to have here. So I have 0.1 liter plus 0.4 liter. equals 0.5 liters. So I know what my total volume of my solution is. So now that I know my total volume of solution, what I can do is I can figure out the concentration of lead, and I can figure out the concentration of sulfate. So see, so it seems like I'm repeating here. I'm doing what I did before, but I'm not, because earlier I was looking at lead nitrate and sodium sulfate. I know the concentration of that compound, but now I'm going to have lead combining with sulfate, making the new solution. So the number of moles of lead I have, 8 times 10 to the minus 4. 8.0 times 10 to the minus 4. And my total volume of solution, 0.5. 0.5. So that's going to give me 1.6 times 10 to the minus 3 molar. And I do the same thing with sulfate. So sulfate, the number of moles I have, 2 times 10 to the minus 3. And my solution is the same here. It's all in one big beaker. So I have 4.0 times 10 to the minus 3. So it's lead and sulfate I'm looking for. Lead and sulfate is the combination that makes a insoluble or not very soluble compound. Now if I look at lead sulfate here, how this all works. Lead sulfate, it can make a solid, and it's made up of lead ions and sulfate. And of course we can see this is a 1-to-1 ratio, right? Because lead is 2 plus, sulfate's 2 minus, so they come together 1-to-1. So figuring out the KSP like we've done earlier is very easy. Lead and sulfate. Okay, so we have that. Now technically what I'm going to do here, I'm just going to call this Q because I know what the KSP value should be. I was given it. In these circumstances, under this temperature, it should be 6.3 times 10 to the minus 7. 6.3 times 10 to the minus 7. So that tells us that to make a saturated solution, when I take my lead concentration multiplied by my sulfate concentration, I should get this. But let's look at our scenario to see what I get. And quite often it's simply called Q. So my lead concentration, 1.6 times 10 to the minus 3. My sulfate concentration, 4.0 times 10 to the minus 3. What I get there is 6.4 times 10 to the minus 6. Okay? Now what I need to do is I need to compare that. Now be careful here, because this means that this decimal is 6 places to the left. This means a decimal is 7 places to the left. So this number is larger than that. So I have more ions than I have to possibly make a saturated solution. So since my Q value is bigger than KSP, PbSO4 will make precipitate. Because that's what it says over here. If my numbers were going to be larger than the maximum amount to make a saturated solution, I have more than I should. So that extra will just fall to the bottom as a precipitate, as a solid. Okay? So it's kind of a bigger question. Please look back at this as you're doing the 4 questions in the assignment. And by the time you get to question 3, it should be a little bit easier. Okay? But again, we're looking at what ions make the partially soluble compound. You'll have 2 things being mixed, and there'll be ions from opposite solutions that'll come together and make that partially soluble compound, the one in which you're given the KSP, and then you have to find out what you get. What would your KSP be? Or experimental Q value is what we kind of refer to it as. And then you can see from there what type of solution. Is there going to be a precipitate? If Q had been less, that means I have less than the maximum, so it'll completely dissolve and I can have more actually to make a saturated solution. All right, we'll see you again.